This paper has two titles. The former title is The Impact of a Coalition, Assessing the Likelihood of Voter Influence in Large Elections. But the informal title, which might be slightly easier to remember, is How Likely Can a Coalition of Voters Influence a Large Election? If you are asked to evaluate your influence in large elections, would you say you have a big influence or small influence? Well, many people think that a single voter's influence in large elections is very small. For example, Condorcet said that, and also the philosopher Hegel also said a single voter would have no significance in large elections. So you may wonder, this seems to be a common sense, but what kind of influence do people mean? And why should we care about the influence being small or large? And if it is small, how small? We use elections as a metaphor for the more general social choice problem. Well, we have M alternatives and we have N agents. Each agent uses a linear order of the alternatives to represent his or her preferences, and the collection of these preferences is called a preference profile, or profile for short. And then, after these agents report their preferences, we're going to apply a voting rule to choose a collective decision. For example, we can use a plurality rule, which chooses the candidate that is ranked at the top most often. In this case, the three candidates have a tie being ranked at the top, and then we're going to apply a tie-breaking mechanism, say alphabetical tie-breaking mechanism, and choose candidate 1 as a winner. Now, if you think about the third voter who actually can influence the outcome by changing his vote from 3 to prefer to 2 preferred 1 to 2 preferred to 3 preferred 1. Because if he casts a new vote, the winner is going to be changed to 2. So indeed, he has influence in this election. And also, if you think more carefully about it, he actually has incentive to do so because he actually prefers the new winner 2 to the old winner 1. This is an example of motivated influence, formerly known as manipulation in social choice theory, which refers to the phenomenon where a single voter has incentive to misreport his or her preferences to make the outcome better for him or her. So why should we care about it? Because people want to design strategy-proof mechanisms where there's no manipulation, and unfortunately, the Gilbert-Satterwhite theorem tells us that there's no way you can do it under very natural conditions. So, if the probability that under some commonly studied voting rules that the profile is manipulable is small, then on the positive side, we don't need to be unduly worried about the possibilities of manipulation, as Platonik mentioned like 45 years ago. But on the negative side, it means that people may have very small voting power, which leads to low turnout. So, the probability of manipulation being small can be positive news or can be negative news depending on the context. It is important to understand how small or how large it is. There's been a lot of work trying to characterize the probability that a single voter can manipulate the profile under a specific distribution called the impartial culture, which is just an ID uniform distribution over all of the rankings. So previous work has established an big O 1 over square root n upper bound for many commonly studied voting rules for any fixed number of alternatives n, and let this number of voters n go to infinity. But the lower bound is much less understood, and the only known matching lower bound was proved by Curtis-Linko about 20 years ago for plurality. And for the other voting rules, the quantitative Gilbert-Satterwhite theorem established a very powerful universal lower bound for pretty much all voting rules, which is omega 1 over n raised to 67. But then there's still a big gap for many commonly studied voting rules beyond plurality when the EC paper was accepted. So the natural question is, are these bounds tied beyond plurality? Before talking about our results, let's first ask ourselves this question. Is the big O 1 over square root n upper bound already small enough? If so, then probably we don't need to worry about closing the bounds. The answer is probably no, especially when the social cost is high. So think about the following scenario. Every time you have seen this negative news about election fraud or someone can manipulate the outcome, you get a utility of -1. But then if you spread this message on social media and all of your friends knows it, and then they also spread this message to their friends, now everyone gets -1, and cumulative everyone would get -n in a well-connected society. In other words, even if the probability is pretty small, like 1 over square root n, and converge to 0, the expected cost per person can be pretty big, which can be like as big O square root n, and it's not clear if it's actually going to be theta square root n. So it is important to understand exactly how small or how large the probability is. And our first contribution is to provide a matching lower bound for pretty much all of the existing voting rules people have studied. And we prove that indeed the probability is theta 1 over square root n. Now you may ask, well, that's just for a single manipulator. What if my friends and I all want to manipulate the outcome? So what is our influence? This was known as the coalitional manipulation problem, which asks the probability that a coalition of B voters who are incentivized to misreport their preferences. And while there's been a couple of papers, there is no known matching bounds. We characterize the probability of coalitional manipulation, CM, by B voters under impartial culture for every single B. And it turns out that for many commonly studied voting rules, the matching lower and upper bounds are the following, which is theta, take the minimum of b over square root n and 1. This is essentially just the theta b over square root n, except that when b is too large, which means that when b is larger than or equal to that square root n, it becomes theta 1. So in other words, every single voter in the coalition would increase the chance by 1 over square root n up to after you have square root n people in the coalition. Now you may ask, what about other kind of influences? What about, for example, margin of victory, which refers to the phenomenon where a coalition of B voters who can change the outcome regardless of their preferences. So while there's been some studies, no matching bounds was known for the likelihood of a margin of victory being B or less. We proved that a similar bound also works for the margin of victory as well as many other commonly studied influence problems. Now you may ask, well, this is only proved for impartial culture, but we all know that impartial culture is unrealistic, which is common sense in social choice. What about other distributions? Especially, what about models beyond the ID assumption? For such models, little was known, and another commonly studied model called impartial anonymous culture was also criticized of being unrealistic. We proved that similar matching bound actually holds not only for impartial culture, but works for a large class of semi-random models, which I'm going to very quickly talk about in a few slides, which seems to be good news. But then you would say, well, there seems to be many results. Did you prove this by boring case-by-case analysis? And the answer is actually no. And the true technical contribution of this paper is an improved polyhedral approach, which is a unified approach that can help us to prove a lot of this bound, makes things a lot easier, and has great potential to analyze the semi-random likelihood of many other things in social choice. Before talking about the model and the proof, let's first take a very quick look of seeing why this is a hard problem, even for two alternatives and ID uniform distribution. So in this case, every voter's votes can be represented as a binary uniform random variable over 0 and 1. So if it's 0, then you're voting for 0. If it turns out to be 1, you're voting for 1. It's not too hard to see that the total number of voters for 1 is an Poisson binomial variable, which is just the summing of all of these random variables x1 through xn. And the probability that this is manipulable without incentives is the probability that this PBB is in the range of n over 2 minus b and n over 2 plus b. So the first trial would be trying to use some central limit theorem, especially Berry-Essien bounds, and that would easily tell us that the probability of this happening is going to be theta 2b over square root n. But then the error bound is theta 1 over square root n, which might be too coarse, especially when b is small. So the actual successful proof was done by the following steps. So for every target value s in this range, we're going to characterize the probability for this PBV to be exactly as to be theta 1 over square root n. So this is easily done for two alternatives by Stirling formula and for uniform distribution. And then the probability of manipulability would be exactly like 2b multiplied by the probability of for each of these target value, which is theta b over square root n. So this seems to be pretty nice and easy, but then when you try to extend this idea to more than 3 alternatives and to other more complicated voting rules, it becomes pretty complicated, and this thing just didn't work out exactly.
We proposed a new and general semi-random model to study the likelihood of influenceability. In our model, there is an distribution adversary, the red guy, who chooses the distributions for every alternative independently but not necessarily identically, each of which is from a set of distributions capital Pi, which is a parameter of our model. And then every voter would generate their rankings R1 prime, R2 prime, all the way down to R prime, Rn prime, independently from these chosen distributions. We call this profile P prime a tentative profile. And then there is a contamination adversary, the blue guy, who can change up to a small fraction, let's say a delta n fraction of the votes at his will, and then the resulting profile P would be used to evaluate the influence. So this model actually combines two existing models. The first one is a semi-random model for social choice proposed in one of my previous papers, and the second one is a celebrated contamination model, which has been very well known in robust statistics and robust machine learning. The proof is done in a way that is similar of how are you going to put an elephant into a fridge. 3 steps. Open the door, put the elephant in, and close the door. Pretty easy. Take collision manipulation as example. We're going to model collision manipulation as something we call a PMV instability problem, which will be defined momentarily. And then the second step, we're going to prove a general technical tool which can be used to solve the PMV instability problem, but also for other problems, we think. And the third step is to apply the tool and characterize the bounds of influenceability. For modeling, let me use a special case of our semi-random model where there's no contamination adversary to illustrate the idea. We're going to model the event that the profile P is manipulable by B voters as a geometric condition which states that the histogram of P is in the union of finitely many polyhedra and can be manipulated into another union of finitely many polyhedra. So what is the histogram of P? So histogram consists of n factorial numbers, each of which representing the number of times the voters voted for a ranking. So the histogram is a Poisson multinomial variable, PMV for short, which is the histogram of the n rankings R1 through Rn generated from the distributions pi1 through pi(n) independently but not necessarily identically. And these distributions are adversarially chosen by the distribution adversary, if we remember. Okay. So, for example, remember that we have 2 alternatives under impartial culture. Then everyone's distribution is a Poisson binomial variable because everyone is doing uniform distribution between 0 and 1. Now, if we think about half of the instability problem, which is the winner was 0 and the winner can be manipulated to be 1 by no more than B voters, then this can be represented as the following PMV instability problem, which is the first PBV is in the range of 0 and n over 2, which means that the winner is 0. And then the PBV value plus B is in the range of n over 2 and n, which means that after B voters change their minds, the winner can become candidate 1. In the second step, we prove an PMV instability theorem to characterize the semi-random likelihood of the PMV instability problem for the influence problem X with budget B we studied in this paper, including the coalitional manipulation and marginal victory. So we proved an trichotomy theorem saying that the semi-random likelihood, denoted by X tilde, there is a tilde on top of it to denote that it's kind of smooths the probability, is either 0 or exponentially small in n, the number of voters, or it's going to be polynomial of two things. Well, the numerator is a polynomial of taking the minimum of b and square root n, and the denominator is a polynomial of a square root n. So in the paper, we characterize the precise conditions for the 3 cases to happen. And basically, these are the conditions that are determined by the geometric relations between two things. The first thing is the convex hull of capital pi, which, remember, is the power of characterize the power of the distribution adversary. And the second thing is this polyhedra. And then, especially in the third part, the degrees in the numerator and denominator both depend on the dimensions of the recess cones of the polyhedra. So then, in the step 3, we're going to apply the theorem to the cases and characterize the result as presented earlier. Okay, so in this paper, we studied the likelihood of influence problems, including coalitional manipulation, marginal victory, and in the paper, other bivariate control problems. So why should you care about them? Because a small likelihood of influence could be good news, meaning that we don't need to worry about the bad things related to the influence, such as manipulation. And on the other hand, it could mean that people would have smaller influences, which lead to low turnout. So good news or bad news, this motivates us to provide accurate bounds on the likelihood of coalitional influence, which is what we did by resolving long-standing open questions as a special case of our more general semi-random model. So basically, our answer is almost theta b over square root n. And if you remember, which says that every additional influencer would increase the chance by roughly 1 over square root n. And this was done by an improved polyhedral approach, which we believe can have other uses. And for future work, I'm very excited about the foundation of social choice beyond worst case analysis. And recently, we have done a couple of works of applying the polyhedral approach and modeling to other problems. For example, condensate paradox, aerodynamic impossibility theorems, likelihood ties, and judgment aggregation, for example, the likelihood of the doctrinal paradox, and also the complexity of winner determination. I would like to mention a few other very interesting papers in this direction, including a recent Wine paper on a different smooth analysis model. And also, last year, there was a nice EC paper on the smooth analysis in failure division. And also, for future work, there are many other applications I'm excited about, for example, multi-winner voting, participatory budgeting, and matching. With that, I would like to thank you for your attention, and please feel free to send me emails if you have any questions.